just imagine if you could pull out the vascular system and put it on the table and examine it in details for any diseases. Now we are using deep learning to do that. So today I'm going to start with the introduction and the importance of human vascular system and the diseases related to human vascular system and the challenges. And then I'm going to talk about three aims. First one is how we can extract the vascular system from the medical images. Second is how we can analyze it for calcification. And the third one would be analyzing it for aneurysm, boundaries, and volume. And then I will talk about impacts and future directions. So human vascular system plays a crucial role in our body. It carries blood from our heart to our tissues. Any pathological implication in this system are critical. Two of these pathological implications are peripheral arterial disease, or PAD, and abdominal aortic aneurysm, or AAA. There are extensive studies that have been done in aorta region, which is before the bifurcation. Very few studies from thoracic to iliac arteries, and we weren't able to see any studies extending the analysis of vascular system from thoracic to patella. So we've done that. The reason we couldn't go any further was the limitation of instrumentation. There's like almost you cannot even see in the images that there's vascular over there to even like annotate it, to teach a machine learning to learn from it. And so the first one is PAD complications. PAD happens when there is arterial narrowing or occlusion from atherosclerosis. The left one is a healthy vascular system. The right one is a PAD. It's a calcium built up on the wall of the vascular system. The more calcium built up, the less blood is flowing through that tissue, and that can cause pain while walking, or in the critical situation, it can cause gangrene and may lead to amputation. So the patient loses the leg. Also a strong predictor for cardiovascular events as well. And the challenges is often underdiagnosed. As many patients, they do not have any symptoms. And it affects 10 million Americans, and more than 14.5% people of age over 69 are affected with it. And it has an average cost of $6,000 per patient per year, or $60 billion annually. AAA. It happens when there is a dilation of abdominal aorta, when the diameter grows over 3 centimeters. As you can see, on the left, you have a normal aorta. On the right, there is a big aorta or dilated aorta. And it's also often asymptomatic. So but when the rupture happens, when the aorta gets very big, it's like a balloon. It's just like rupture happens. 80% of the patient die. And the challenge we have is most of the radiologists, they analyze it just based on the cross-section diameter, one slice of the medical image, and diameter of the aneurysm. And it's estimated that 2.2% American has AAA with a cost of $9.6 million per patient, total cost. The background work, Laure has developed a CNN-based hybrid system, and they could achieve 82.6% dice accuracy for aorta to iliac artery segmentation. That 82.6% is important because we could improve that to 83.4%, and not only that, we could also extend the area from aorta to iliac to aorta to patella, which is like extended region. And it will also automatically quantify calcification. Our contribution for vascular segmentation is we achieved a state-of-the-art accuracy in vascular segmentation and extended the segmented region down to femoral arteries. And for peripheral arterial disease, we built an ML model to automatically quantify vascular calcification, and we validated the accuracy against the expert evaluation. And for abdominal aorta aneurysm, or AAA, we designed a multi-stage ML system that detects aneurysm boundaries and estimates aneurysm volume in a zero-shot setting, so without training data. So these are the aims. The first one is, in order to analyze the vascular system, we need to extract them. So we develop robust vascular segmentation models. Second one is we extract the peripheral calcification scoring of peripheral calcification, as you can see. And third one is we analyze the aneurysm, as you can see in the last image, where there is no label data sets. Preliminary results so far and resources. At the Dr. Valafar's laboratory, previously there was a research that uses unsupervised object tracking to identify arterial structure with 85% agreement. So identifying that means like two arteries here or three arteries, and they are validated against the expert. The resources we have available, we have access to 72 AAA patients scan and 27 femoral endarterectomy patients. And annotation, 11 out of these 27 are have pixel-wise annotation. We actually performed that. And then 16 out of 27 have manual calcification score, one integer representing all the calcification happening in the vascular system. And 72 have annotation for the boundary of the aneurysm. Actually, this is a better picture showing the resources we have for endarterectomy patient. For 11 of them, we have the pixel-wise segmentation. For 16 of them, we have one integer representing all the calcification happening in the vascular system. And for aneurysm, we have two integer for each scan representing the beginning and end of the aneurysm. I'm going to pause here if there's any question. Okay, perfect. And so the first objective is to extract the vascular system, to enable that analysis of the vascular system. So here we have a specific situation, we have a data. So we need to be careful with the deep learning models we're using. It cannot be too complex, it cannot be too simple, something in between. So first, in order to achieve that, our plan was to annotate data from 11 patients that was mentioned in the resources. And then we need to pre-process and augment the data. And then train and validate CNN and transformer-based model. So we want to focus on these three. And then evaluate the performance. We were able to finish all of these tasks. And then for the models, we focus on the unit and TransOnit. TransOnit is a model that we designed, and I'm going to talk about. So for the pre-processing and augmentation, we needed to normalize the intensity range to a standard scale for the images, and rescale and resize and convert data to a format that matching the model's training conditions. And for augmentation, I needed to study all the data sets in detail to understand what augmentation techniques applicable here and what is not. Because we couldn't use vertical flip. That would be a bad data for training. So, but after experimentation, we decided to do contrast limited adaptive histogram, equalization, blur, horizontal flip, grid distortion, downscaling, random brightness, and contrast. These augmentation help to augment the data and in our training process. The results. So we focus on two machine learning models. First one is UNIT. Why UNIT? Because it performs very well on a limited data set. And structure is very well known, but I'm going to go quickly over it. So we have an encoder decoder. For encoder, we use a pre-trained ResNet34, pre-trained on ImageNet datasets. Why ResNet34, not higher or lower? Because based on the resources we had, limited dataset we had, we didn't want like make it more complex that it wouldn't be able to perform well on this dataset. And then, so encoder extract the features, it downsamples, and then it passes it through the bridge, which is a convolution layer, and then it passes it through an upsample, and it creates the output image. And there is a skip connection between the encoder and decoder throughout the process. UNIT is pretty good at extracting the high resolution spatial information, but if we look at the vascular system, there's a continuity in it. So that motivated us to use transformer too. So what we did, we took out the bridge out and we included transformer there with the multiple, like desirable number of transformer as a designer can decide that is L. And pretty much for the rest of it, we used the same encoder and decoder here too. And for the L, we chose 1. So here the goal is UNIT extract the high resolution spatial information, and transformer learns from the global context of these extracted features from the encoder. And so, yeah, actually, after training these two models, we were successful in segmenting the vascular system beyond the iliac artery to patella too. And yeah, we were able to publish the results in 2 conference paper and 1 journal paper as well. So we use a 4-fold cross-validation to compare these two models. And TransOnet was able to achieve 80%, 80.64% dice accuracy in the 4-fold average of all the folds. So what we are looking at here, this number is extracted from the average of the purple bars. We can see it underperforms on the fold 4, and I'm going to talk about that. But UNIT was able to achieve 83.4%, and was a state of the art. The other paper was 82.6. Not only we extended the region, but we also improved the accuracy. Here we're looking at the yellow bar, and which in average you always have the higher accuracy than the TransOnet. And on the 4th fold, you can see we only had 2 patients for testing, but we used like 9 patients for training and validation and 2 for testing. That was one of the reasons. So it overfit on the training data and underperform in the testing. And why TransOnet underperform here? That was a question I asked myself. Well, how can I improve the TransOnet? The idea is good, like we get the global context. But there's one thing, limited data sets. Transformers are data hungry, whereas convolutional neural network is not as much. So UNIT was able to outperform TransOnet, but there are ways to improve it. And I'm going to talk about it in the last section. So let's putting aside all the numbers and visually inspect how the model performs. This is the input images of the medical scans of the patients. And voila, the model extract the vascular system. So now extracting the vascular system, the next goal is analyzing calcification happening in the vascular system. The hard part was extracting the vascular system. Easier to extract the calcification now. So for this AIM, first we apply the model from AIM1 to extract the vascular system, then overlay that to the input image to extract the exact vascular system, because the output of the model is only 0 and 1. So we multiply it by the input to extract the vascular system. And then after that, we apply thresholding to identify calcification, and we develop a calcification scoring model to output one integer representing how much calcified those vascular system is. And then at the end, we validate the results against expert manual scoring. And we were able to finish all of these tasks. So pretty much, this is the visually inspecting the performance of the model, image sequence, and then the model from AIM1 extracting the vascular system. Then we multiply that into the input image and apply thresholding and apply calcification scoring technique, the methodology we developed to have this vascular calcification extracted. And after that, we apply calcification scoring methods to have a number. And of course, there are like more systematic way we could extract the vascular system. We could also use intensity distribution of the pixels to find which one is representing calcification and which one is just the normal vascular system. Here, the result. 16 patient, the model from AIM1 never seen in training, validation, nor testing. And the model from AIM1 applied to these 16 patients. You can see the amount of calcium score of these 16 patients ranges from few hundreds cubic millimeter all the way to 25,000 cubic millimeter. And the model was able to predict the calcium score of these patients with the accuracy, with the R score of 97.8%. Robustly. I'm missing something. I might come back. Yeah, is another way to look at the data. So the blue represent how much calcification that patient has, whereas the orange shows how much calcification is predicted using our approach. You can see they are following each other pretty closely for very low calcification, which are like G10, all the way to high calcification patients, which is R12. And the mean absolute percentage error is 9.5% here. I'm a big fan of visualization.
Alireza, if I could ask a clarification question. The comparison of your results, is that sort of, what is the sort of gold standard here? Is this based on the interpretation of experts, or is this based on some other ground truth like dissecting or surgical exploration of the calcification in arteries and veins?
A great question. Thank you. So an expert went through all the scans, medical scan, and manually measured the amount of calcification in patients. That's how the blue is extracted from each patient. Does that answer your question?
That's perfect.
Yeah, thank you. So I'm a big fan of visualization. So let's take a look at the patient R12 and B14. R12, which has the highest amount of calcification, and B14 is like relatively low. Here we have the image sequences coming in, the model for AIM1, extract the vascular system, and then we extract all the calcification happening in these systems. And we can also take a look at it in cross section. Here, we can take a look at the performance here in cross-section. The red shows the vascular system, whereas the blue is a calcification. Blue might be a little blackish, but we can see the blue happens on the edge of the vascular system and on the around it. We're in the aortic region. Now it's a bifurcation. We go to two separate ways, and then you can see he takes the calcification. Now we're in the iliac area. And as we go down, the model robustly tracks the vascular system as well as the calcification. Now we are in the femoral region. And almost getting to patella here. As you can see, the size of the vascular system becomes very small as we get to patella. And just imagine after patella, it becomes very, very small. Some of the times, even the instrumentation doesn't capture it anymore. Okay, no, wait, pause here. Is there any question? Yeah. Cool. And so the last aim, the most challenging aim. For aneurysm analysis, we didn't even have annotation, pixel-wise annotation. So how are we supposed to teach ML to extract something that it doesn't know, hasn't learned or trained on? And for the aneurysm, our goal was, how can we measure the volume of aneurysm? So in order to do that, first we need to extract the vascular system, including the aneurysm. Second, we need to detect the boundary of aneurysm. And when we do that, only then we can measure the volume of aneurysm. So three goals here. So our plan was, let's apply the model from A1 here and see how it performs. We learned something very interesting here. So like model from A1 segments the vascular system when there is no abnormality, but as it sees as segmentation. As you can see on the image, the red is showing the segmentation, but the middle one, which is like a balloon, is an aneurysm, but the model didn't do any segmentation in that region. That kind of motivated us to do a little analysis. We trained a model on the output of the units, and we pooled 16 endarterectomy patient and 16 aneurysm patient, and we trained the model to predict if this patient has a healthy vascular system or like aneurysm, like abnormality or not. And it got a very high score. As a matter of fact, one of those endarterectomy patients had aneurysm, but it was not categorized correctly. But the model was able to categorize it as aneurysm, and it was correct. And so after doing that, we learned the model from AIM1 freaks out and doesn't do any segmentation when it says abnormality. What can we do? It's like we come up with the object tracking. Whenever it stops doing any segmentation, we use object tracking to follow that same intensity afterwards through the aneurysm. And then when we extract the vascular system, now we need to find a boundary of vascular system. So we plan to use LSTM or rule-based heuristic to locate the boundary of aneurysm. And then we want to validate, since we had annotation for those, we want to validate our accuracy against the expert manual. And then at the end, we can perform volumetric assessment of the aneurysm volume. And we were able to finish all of these tasks. Some of these I proposed in my proposal defense. I did the first one, but I proposed that I'm going to do this res. So I finished those. And so this is the diagram of how the model works. Unit finds the location prompt of the region that fails, like before the region, and then SAM2 tracks aorta across the triple A or aneurysm, and then we have, so first two steps, we have vascular system extracted, and then we have two approaches to detect the boundary of vascular system. One is expert system, and the other one is LSTM. I use USE and USL. Those acronyms are very important. Those are representing the approach we use, different approaches. And after detecting the boundary and having the vascular system, we can measure the aneurysm volume. So we use SAM2 for tracking. SAM2 was way better than SAM1, and Meta improved the model and they trained it on much more data. And it had a zero-shot generalization capability, and it was robust to anatomical variability from one patient to another, and also like one scan instrumentation to another instrumentation. And so this is the result of it. So we have A, and the model unit plus SAM2 was able to extract the vascular system, and we can see we have extracted in the C, we have extracted vascular system. Now the goal is to find the boundary of aneurysm automatically. So for that, we use two approach. One is expert system, second is LSTM. Expert is a USE or use, or LSTM and USL. Expert is good. It's very interpretable because we say like, in order to develop the expert system, I did a grid search. I like multiple variables to train the grid search. And so it says like if the size of the aorta increases 20% for 4 consecutive or 3 consecutive slices, that is a sign of the beginning of aneurysm. Whereas the same thing happens in the end, that would be the sign of the end of aneurysm. And I use a grid search to find those variables, the value for those. LSTM was like, okay, there's a sequentiality here. Let's train an LSTM to learn from sequential data. What we learn is the expert system outperformed LSTM and achieved an R square of 71% to detect the beginning of aneurysm and 76% for the end of aneurysm and 92% for the volume. Here's how it performs. On the left, we have number of segmented pixel per slice. The left of the plot shows like thoracic region. As we go down, that's like bifurcation. And the blue represent the number of segmented pixels per slice. So you can see like it starts like 1,000 to 2,000, and then when it gets to aneurysm region, we have a spike of number of segmented pixels that represent the aneurysm. And we can see that that happens in other patients too. So that was the intuition. So I was like, we can use expert system, and we defined variables to detect the beginning and end of the aneurysm here. And since there's a sequentiality here, we can also train an LSTM to learn from sequence data to detect the boundary of aneurysm. So, and on the right is a volume predicted by the expert system. You can see the volume of aneurysm ranges from like 50,000 pixels all the way to pretty big 35,000, but still the model was robust to predict the volume of aneurysm. So since there was sequentiality of data, we wanted to try LSTM. Let's see the performance of LSTM compared to use here. From the top figure, the left is LSTM, whereas the right is expert system. You can see expert is very robust. There's a little more error for the beginning and less error for the middle, the blue represent the middle, blue represent the end of the aneurysm, and the green very robust for the volume of aneurysm. The reason LSTM did not perform, we studied this very details too, is because LSTM is data hungry at the end of the day. And 72 samples was not enough, even though we used cross-validation to rule out like what if like portion of the data was not good that we tested on it. So we used cross-validation to rule that one out. But it's still, I think the amount of data was not enough. We could have used transfer learning. That could be something to do in the future. So that's pretty much, we were able to do the aneurysm analysis too without any training data. The broader impact of this research. We had a collaboration with medical school, and they tried different drugs to see which one of them is alleviating PAD situation. But the way they analyze the mice is like they dissect mice. Like they take images too, but they need to go through the scans to measure the amount of calcification happening, or they need to dissect the mice to see like how much that drug was effective to reduce the PAD. But with the approach like ours, they can do it in a matter of seconds, very fast and accurate. The future direction. What we've done can be improved too. Nothing's perfect. For the segmentation, we didn't get the chance to fully explore sequential models like LSTM. LSTM is pretty good at capturing spatial and temporal dependencies, and for the vascular system, that exists. But the limitation with that was a large data set is required. And also transformers, good at capturing global dependencies. We only explored one variation structure of transformers, TransOnet, but there are many more structures that could be explored that we didn't get to do that. And for the limitation, we could always like pre-train it on large data set, find a data set that is close to our data set, and pre-train it on that, and start fine-tuning on that for vascular segmentation. For deeper vascular analysis, we can integrate more clinical relevant data for better care. For example, we can combine vessel level metrics, like what percentage of the vessel is blocked. That can have a correlation with the leg pain potentially, or like mobility of the patient. And for AAA analysis or aneurysm analysis, we can take a subset of the output of SAM2 and have an expert to correct the output and use the output to fine-tune SAM2. And I'm sure it's going to make the SAM2 to perform better for segmentation. And we can also add more regional prompts from unit to SAM2 for better performance. One thing that we observed from SAM2, our unit did pretty well for lower vascular system, like from after iliac artery. SAM2 performed poorly. So we could not use SAM2 for vascular calcification. Not the way we did it for aneurysm, at least. And we can also use attention maps for clinical trials. And I would like to use the opportunity to thank mentor, research collaborators, and funding sources for the support, absolutely, NIH and NSF. And committee members, thank you so much. Supervisor, super grateful. And colleagues from room 2238. And Dr. Zan Laboratories, thank you so much. And the flowers. And yeah, the coffee. Thank you so much. And that's one,